Good. So okay, so let me briefly recall what we had last lecture 2 weeks ago. So as usual, we have our Quiver Q, and consisting of the set of vertices, set of arrows. So well, we've defined for a vector D in z greater than 0 to what? So this is the dimension vector. So we've defined the corresponding representation space E sub D. So this E sub D is nothing but the direct sum over all arrows from spaces between K to G S of alpha and K G T of alpha. So this is the representation, and clearly the dimension of E sub D is the sum over all the arrows Di Dj. So this is the space. So this is just an affine space, very simple. And we also have the product of general Lilian groups. So this is G sub D. This is the product over all vertices GL Di. Clearly the dimension is sum Di squared. Yes. Okay. And then this group acts on the representation space, and for representation M in ED. So we considered the corresponding orbit of M, which is just GD orbit of the representation M. Good. Okay, so far it's fine. So we've also defined the quadratic form of the Quiver. Of Q. So this is by definition, yeah. So we take for Q in Z2 Q naught. Maybe, sorry, Q is a bad notation. So for X. So we consider Q of X to be the sum over all vertices xi squared minus the sum over all arrows so I to j xi xg. Okay, so I think this we had last time. Let me check. Yeah, I think we did, but nevertheless, let's repeat. So this is the quadratic form of the Quiver. And let's define two other forms which are of use for us. So these are bilinear form, first of all. So let me define, so we take x and y from z to q naught. And for these two guys, we say that xy is, by definition, u of x plus y minus u of x minus q of y. Yeah, so this is just the definition of the bilinear form. And let's compute it explicitly. So it's a kind of computation. Wait. So let's let nij. Yeah, maybe before that. Sorry. One remark that the definition of Q, sorry. So the definition of U does not depend on the orientation. Okay, so the only thing which matters is the number of arrows between the vertices. So let us define notation. So let nij be the number of vertices between the number of arrows, sorry. Between vertices I and j. Something is wrong with my pen, sorry. It's not ing. Okay. So then let's do two computations. So the first computation is what is q of x? Yes, just it's not even a computation, but just the rephrasing of the definition. So this is the sum xi squared overall I minus the sum again over the now pairs of vertices, and let us order the vertices in any way, so doesn't matter how, any order. And then I put here nij xi. Okay, so this is just the again observation that nothing depends on the orientation. The only thing we care about is the number of arrows between two vertices, and this order is needed only because we don't want to write twice the terms corresponding to each arrow. Okay. And this is the first computation. Then the second computation is for the bilinear form xy. So maybe somebody can tell me what is that. So how to write down the value of xy in terms of nij. So just by definition, this is q of x plus y minus q of x minus q of y. So what is then the value of xy?
Maybe it should be something like the second term in Q.
Well, but it should depend on both x and y.
Yes. I mean, we should change, take sum over all pairs and change xj by yj to say.
Well, this is close, but
it's just a guess.
Yeah.
I suppose it should be 2xi, yi in the first sum.
Okay.
Then in the second sum, I think we just get nij xi yj plus yi xj.
Yeah, so I just write it like that. Okay. So the claim is that the value of the bilinear form on two vectors is twice the sum xy yi minus the sum over all non-equal pairs ij, but well, it's important that we compute 2 times each pair. Yeah. So because we have xi yj and xj yi, these are 2 different things, right?
May I ask, here we consider also only quivers without loops, or?
Yes. Let's write this. So remark. So no oriented cycles. Okay.
But we don't have any orientation, so it's just.
Yeah, let me think a bit.
No cycles.
Let me think a bit. No. Well, I mean, in principle, maybe let us work out an example. So I think it's still fine. So maybe we don't need. So an example. So let's Q be Quiver, just one loop. So by definition, what is Q of x?
Just 0?
It is. And what is Q of xy? Oh, just xy.
0 as well.
Yeah. So it doesn't make a problem here. Yeah. So, well, it's 0, but I mean, it is something reasonable. Yeah. So we don't impose this condition, at least so far.
So is it true that in case of when we don't have cycles, Quiver, this like bilinear form will be non-degenerate? Yes.
No.
Okay.
Well, well, we'll formulate some condition, yes, but I think even without cycles, Yeah, even without cycles, the form can be degenerate, I think. Yes, I think it can. So maybe the simplest example. Yeah, let's see. So work out an example. So let's consider just A2 quiver. So what is then XY? Just by definition.
So 2x1y1 plus 2x2y2 minus 2x1y2 minus 2x2y1. Oh, is there two in the last?
So do you need these twos?
Maybe we don't need the last two twos. Yeah,
Let's
I don't think we need.
So we don't, yeah?
Yeah.
Okay.
I suppose we shouldn't have one of the last two terms if we. Maybe I don't understand what is Nij then.
Okay,
Well,
so let's compute it explicitly. So what is Q of X? By definition, this is x1 squared plus x2 squared minus x1, x2, right? Now,
sorry, it should be symmetric. Yes. Okay.
Okay. Okay, maybe let's finish the computation. So Q of x plus y minus Q of x. Q of y is what is so x1 is y1 squared, y2 squared, minus y1 x2 plus y2. Okay, and then we subtract x1 squared, subtract x2 squared, subtract y1 squared, subtract y2 squared, and add x1, x2, and add y1, y2. Okay, and then we get exactly the result which is written upstairs. So is this form non-degenerate or degenerate? So let's check this.
I think it's non-degenerate.
Why?
Because it's represented by a matrix 2, -1, -1, 2.
Absolutely. And it's non-degenerate, right?
Yeah.
However, so in principle, so can we make this? So let's consider another example.
But maybe we can just add an arrow and we will have the same on the left, but we'll have the -2s.
Yeah, so this is what is called Kronecker quiver. Okay, And then, so our xy now is twice x1, y1, x2, y2. And then now we subtract twice xy1, 2, x2, y1. Okay. So what is the kernel of this form?
When x1 equal to x2.
Absolutely, yeah. So if x1 is x2 is 1, then xy is 0. Right, just by definition.
Why do we get Cartan matrices?
You mean upstairs?
No, in case of one arrow we got Cartan matrix like 2
Yes.
minus 1 minus, and here we have like a fine version of how to say.
Yeah, but actually, this is one of the points. So we'll discuss this so that the definition for this quadratic form is very closely related to the Cartan matrices, to the Lie algebras, and so on. So this Gabriel's theorem, which I mentioned at some point, says that the indecomposable representations of the ADE quivers, they are kind of in one-to-one correspondence with the roots of the corresponding Lie algebra. And this is the definition of this one of the ways how you can define the Cartan form or the killing form in the Cartan matrix for the corresponding Lie algebra. But we'll get back there. But you are absolutely right. So this is exactly the Cartan matrix.
Okay, thank you.
Okay, so these are some examples, and you can see that even for a simple quiver, this is some, well, it might be not that trivial. So maybe the last definition, which is also kind of important for the story, this is what is called the Euler form. So the Euler form is defined on the same space. So we take x, y from Z to Q naught. And we say that xy is the sum xi yi minus the sum over all arrows x I y. So can I explain the difference between the Euler form and the form defined above?
At least this form is not symmetric.
That's right. That's right.
In general.
That's right. So this form does not have to be symmetric. Okay, but still it's useful sometimes, so we do consider it. So maybe a last example in this part. So if we take U to be just a 2 quiver, then the Euler form is x1 y1 plus x2 y2 minus x1 y2. Like this. Okay. Okay, let's proceed further. Yeah, maybe yeah, okay. So yeah, let's formulate a couple of properties of the form explaining why we are interested in it. So the first property I think we mentioned last time, again, let me check. Yeah, probably we did, but nevertheless. So let's formulate this as a lemma. So let us take D to be vector in Z greater or equal to 0 to Q. So then U of D equals to dimension from M minus dimension of fixed one M for any d-dimensional U module M. Okay, so this is some well, in principle, definition of the form is purely combinatorial. However, it does have a relation to the representation theoretical construction, so it can be just restated in terms of the dimensions of home and X spaces. So I think we were not able to prove it 2 weeks ago, did we? So did we prove it? So somebody remembers?
No, we haven't.
I forgot.
So we just formulated it and we didn't prove it. So let's do. So let us use the short exact sequence. Short projective resolution. For M. So recall that we have the following exact sequence: 0 to direct sum overall arrows. Okay. D I P J, and then direct sum overall I. Di P of I, and then to M, and then to G. Okay. So now, do you have any ideas how we can use it to compute Q of D?
Maybe we can take homes to M of all of this.
Yes.
Or maybe from M, it's a bit
Well, actually,
hard to choose.
like your first idea. So let's apply this home factor. So how does it work? So first of all, it reverses the arrows, right? So therefore, we have following sequence 0. So home MM. and then di p of m, and then we have direct sum overall arrows I P of J like this M, and then oops, x1 M. And what's the next term?
0.
The next term is 0. Please raise your hand if this is clear, or we better discuss it. Yeah, so this is 0 because the x from the projective module to somewhere is always 0. Yes, so there is no way to non-trivially extend anything with a projective. So this is 0. So now let us write down the dimension.
Sorry, I thought it is just definition of X, no? Okay, maybe.
What do you mean?
I mean, we defined X as like quotient of like home to P1 by home to P0 from N as, or maybe not to N, as I remember.
Yeah, I agree. This is also true. Yeah. In principle, yeah. You're absolutely right. So now let's write since we have this exact sequence, then if we take the dimensions of those spaces with the alternating signs, then we get 0. Okay, so I mean that the dimension of home from M to M minus the dimension of the second space plus the dimension of the third space minus the dimension of the fourth space should be 0. Okay, so let's write this. So first of all, we write this dimension home MM minus the dimension of home DIPI to M. What is this? So I mean this dimension of this space. So we have the direct sum over all arrows, and then we have homomorphisms from GIPI to M. And then we want to sum up the dimensions of these homomorphism spaces. So what is that?
Such homomorphisms are defined by images of, I don't know how to call these vectors, like generators of P of I.
Yes.
And there are like DI generators at each vectors. So for each of them we have DI coordinates. So this is DI square for a given in each vertex. So it's sum of DI squares probably.
Absolutely. So this term gives us the sum of di squares because, let me repeat, as Andrei said, we only care about where the generators of pi are mapped to. And since the dimension of mi is di, this was exactly our choice, we have this sum di squared. Okay, so now we are interested in the third term. So what is the dimension of the third term?
Wait, now I'm a bit confused. I thought
Yes.
M was a representation of a quiver.
Say it again, please.
I thought M was a representation of a quiver, but there can be some arrows.
Arrows where?
It's
So I just didn't get your question. So could you please?
no. I think I get it now. It's the dimension of the
So our M is any representation of Q with the property that the dimensions of the spaces are exactly Ti. And otherwise, of course, in there might be arrows in Q, and well, M is arbitrary representation, but we just fixed in dimension.
Yeah.
Okay.
Yeah.
Okay, now let's compute the dimension of the green space.
Probably it is the sum over all arrows from I to j of di dj.
Okay, and then we are left with a negative dimension of x1. And this sums up to 0 because the sequence is exact. So this is our conclusion, that the value of Q on D is exactly dimension of home spaces minus dimension of X spaces. And just this is the notation that sometimes this is denoted by M capital 0, upper index 0 minus M upper index 1. This is just a notation. So the corollary, which somehow the direct corollary, but a bit unexpected, that the so the difference between home and dimension of home M and dimension of X M does not depend on the representation. So only on the dimension vector. So you see, and this from the first glance, this does not seem to be evident at all. Okay, so that's it. And one more thing where the quadratic form of the quiver pops up is the following formula, which is going to be rather important for us. So the formula computes the codimension of the orbit of M. Okay, so we take M to be some representation of our quiver, and then recall that we have the representation space ED, and in this representation space, we have the action of the group, and we want to compute the orbit. So how to do this? The claim is that there are two actually ways to write this. So first of all, this is the dimension of endomorphism M minus U of dimension M. Or in other words, so how can we write down this difference? So is there some short way?
dim of X.
Mhm. Mhm. So actually our lemma claims that so if you have no extensions, self-extensions, then the orbit is of codimension 0, so it's a kind of the very large one. But the larger, the more extensions you have, the smaller is the orbit. Or you can rephrase it as follows. So you can study the endomorphism spaces, so the homomorphism from M to itself, and then you are saying that you better have no endomorphisms, or the endomorphisms should be as small as possible in order to make the orbit large. But if you don't have endomorphisms at all, so then the orbit is large. Oh, small also. So the codimension is more or less the dimension of endomorphisms, or otherwise the X groups. So let's prove this. So just by definition, codimension the orbit is the dimension of ED minus, yeah, maybe I should have written as usual, G is the dimension of M. Just for brevity. So minus the dimension of the orbit. Okay, and so by definition, the dimension of ED is the sum over all arrows di dg. This now minus the dimension of the orbit. So what is the dimension of the orbit? How can we compute it? So do we have any control on the size of the orbit of the representation?
Yeah, we should have some control, say, if the map suggests 0, then we can have some more freedom to.
Yes, but is there some formula we can write for the dimension in terms of M, in terms of some characteristics of M?
Well, it's the dimension of GLD minus dimension of stabilizer.
Yes, by definition, so this is dimension of the group minus the dimension of the stabilizer. Like this. So maybe before writing this totally, so let me write that dimension of this guy is the sum ti squared. And what is the dimension of the stabilizer?
Maybe it is the dimension of endomorphisms.
Yeah, so actually you're absolutely right. So by definition, this is the dimension of the automorphism of M. Yes, because
of automorphisms.
yes, but actually you are, so what we need is that this is the dimension of the endomorphisms. Yes, and this is clear because the automorphisms are open subset in the space of endomorphisms. Therefore, their dimensions coincide. And now we conclude this is the sum gi to g I to g minus sum gi squared minus plus m0. And that's what we want, because this is nothing but dimension of 0 minus q.
Sorry, may I ask about this point when we identified dimensions of automorphisms and endomorphisms? Why it's open subset? We have like condition of commutativity with many operations, so it's not like just embed matrices to matrices, but at least it doesn't seem like that.
So indeed, so what are endomorphisms? So these are collections of maps between the spaces. So I mean, for each vertex, we need a map from the corresponding mi to itself, and we have this condition that the square should be commutative, right? Now, what's the difference between endomorphisms and automorphisms? The only thing is that we insist that the automorphisms, they have to be invertible, right? So this means that each map has to belong to GL GI. Yes, so there is some point, yes, here. So in other words, you take the endomorphisms and you intersect these endomorphisms with the GLs of GI at each vertex, right? And the claim is that the dimension does not drop, right? So,
so it's like some linear independency between like differential of determinants and maybe some these equations which define subsurface of endomorphisms. So why it is independent?
So 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 it's not like an independence, but this says that how to say yes, that if you consider the endomorphisms of M, yes, then the condition that the maps are non-degenerate, this is still an open condition. What can be the argument? So does anybody know some simple direct argument? Let's see.
Well, endomorphisms are the tangent space to the group of automorphisms.
Yes. So, but the group, so yeah, but how to say, mm, so there is still some so what you said is somehow still, if we want to prove this, yes, this statement, we still need somehow to show that the condition of the maps of an endomorphism being non-degenerate is still an open condition.
The condition of non-degeneracy of some endomorphism, is it just the all maps, the all maps acting on each mi should be non-degenerate? So we have just equation of determinant of all determinants should be non-zero in each vertex.
That's true. That's true. Yes. But what Andrei is asking for, so he's just, let me kind of say it in a very kind of stupid way. So I mean, we can imagine, so suppose we have algebraic relations cutting out the endomorphisms of M. Yes, so these are those commutativity conditions. Yes. So why it's impossible, for example, that all, so if we take a solution of these equations, I mean of these commutativity equations, then each solution would be represented by a degenerate operator. So I mean, why we can't have a situation when each solution of the commutativity conditions have some degenerate operator at some point, at some vertex.
Okay, so you say that we have a condition of commutativity and condition
Yes.
of non-degeneracy.
Yes.
And and why that conditions are, so why the corresponding solutions intersect
Yes. Yes.
transversal.
This is what Andrei is asking.
So I mean, maybe I don't understand, but there's a concrete homeomorphism between the some open neighborhood of identity in automorphisms and some open neighborhood of zero in endomorphisms given by exponential and logarithm.
So we take out automorphism of M, and we take endomorphisms of M. And what Dima is suggesting is that we can take zero here and the identity here. And then there is a map. Yeah, maybe indeed this is the simplest way. There is a map exponent which maps this guy to this, right? So if you take a collection of maps, endomorphism maps, and you exponentiate each of them, then what you get is an automorphism, and the dimension is the same. Does it sound fine? So I think it seems good.
So yes, I like this argument, and it seems like this somehow a bit complicated question of solutions of commutativity equations is somehow hidden in fact that we have structure of Lie group on automorphisms, which follows from fact that this is stabilizer. Something. Okay, thank you.
Okay, so let's proceed. Let's proceed further. Yeah, maybe one important corollary here, even two corollaries. So the first corollary is as follows. So assume that Q of D is less than or equal to 0. Then there exists infinitely many let's see what should I start with. Yeah, infinitely many isoclasses of d-dimensional representations. So how can we show that?
Sorry, shouldn't it be strictly less than 0, or maybe?
Well, let's start with this case. So assume that it's less than 0, then how do we proceed then? So actually, less or equal to 0 is enough, but let's assume that it's negative. So then what do we do?
Use our formula for codimension, or
So codimension of M is Q D minus dimension of so show it. So it's the formula, yes. So we have the difference between endomorphisms and Q of D. Okay, maybe I write it here. Dimension of morphisms. And so if we know that the Q of D is non-positive or even negative, so how do we argue then?
then we have like continuous family of non-equivalent representations, since
Yes. Why?
since we can't like cover all E of D by finite number of orbits of codimensions more than 0.
Yes, yes. So indeed, so the only thing is that we better have the dimension of the endomorphism space to be positive. Yes. So is it necessarily positive or might be 0? So of course it can't be negative.
Okay, it can be constants, probably.
Absolutely. So since lambda times identity always belongs to endomorphism of M, the inequality U of D plus epsilon 0 implies that for any M from ED, the codimension of EOM is strictly positive, and therefore there are infinitely many orbits. In ED. Or, well, since we know that the orbits correspond to Isaac classes, therefore the number of Isaac classes is also infinite. Okay.
So moreover, we have several lambdas in case of several vertices, and it should give us some restriction on Q
What do you
of
mean?
D if you want.
What do you mean several lambdas?
I mean, if we have several vertices, we have several spaces. What is endomorphism? It is several maps, and each of them can have different scalar lambda, right?
Yes, but we don't know anything about the endomorphism space. So in particular, there might be no endomorphisms, but the scalars.
Yes, but at least we have this dimension is at least number of vertices. I mean only this.
Why? I didn't get it. Why?
Because we can embed here family which consists of this with different lambdas. No.
Let's work out an example. So if we have, say, P2, and say M is just, I don't know.
Sorry. It was
squared 2k squared, and the identity map here. Yes, so we need k squared is our M, and then we have another M. And then we need the homes from here to there. So if we take lambda 1 here and lambda 2 here, and if the maps are identities, then you see that the square is not commutative outside the case lambda 1 is lambda 2, right? So does this make sense?
Yes, my bad. Sorry.
Yeah, so, but at least if lambda 1 is lambda 2, then everything is fine. Yes. Okay, so one more corollary, which is somehow absolutely obvious. So another corollary says that, so assume U of D is less than 0. So then the number of Isaac classes of indecomposable U modules is finite. Okay, So you see, it's kind of this statement is close to what we've just proven, but it's a bit different. Yes, so it says that if you found any vector D such that Q of D is non-positive, then the number of isoclasses in decomposable Q modules, is infinite. Sorry. So why?
If it is finite, then any representation due to Krull-Schmidt theorem, due to Krull-Schmidt theorem, any representation is sum of decomposable ones. Then we have like parameterization by several integer numbers, less, more or equal to 0, greater than equal to 0. So if we have this finite numbers, we have like discrete, how to say, discrete family of orbits of codimension at least one, which also not covers all ED.
Well, I mean, you're right, but we can say even simpler. We know that if Q of D is non-positive, then the number of isoclasses of D-dimensional representations is infinite. But if we had only finite number of indecomposables, then the number of ways you can get a D-dimensional representation as a direct sum of those indecomposables would be also finite. Yes, because well, if you have finite number of objects, you can cook up only finite number of sums of a given dimension. And so if number of decomposable representations is finite, then for any fixed D, the number of isoclasses of D-dimensional representations is finite as well. Okay. Good. So you see, this explains why the study of this form is that important. For example, we know that if you are able to find some D such that Q of D is non-positive, then you are somehow done. So at least, I mean, if you are interested in the question when, so our question we are going to study to describe all quivers with finite number of indecomposable representations. Yes, so well, the answer is given by the Gabriel's theorem, which says that these are only AD type quivers. And well, we see that the form is important, for that. So let us study it in more details. So let us prove the following lemma. So the lemma says the following. So we have U to be connected Quiver, and D is a vector in Z greater than 0 to 0, such that Q of G is, or maybe even, right? So let us formulate it in terms of the bilinear form. So such that dx is 0 for any x in Z to Q naught. Okay, so we assume that we are able, so recall that this is the symmetric bilinear form defined by our quadratic form. And we assume that we are able to find a kernel, this form, maybe let me. So this like what Andrei asked at some point, so whether the form can be degenerate or not. So let us here just assume that it is degenerate. And let's try somehow to understand what does it mean for the Quiver. So then the following holds true. So first, U is positive semi-definite. So in other words, if you substitute, if you take Q of X, then it can't be negative. Then second, Q of X is 0 if and only if X is proportional to G. And then finally, DI is non-zero. So this means that the kernel of our symmetric form is something with all coordinates being non-zero, and actually this kernel is one-dimensional, and if it exists, then the form is quite good in a sense. Well, at least so we see there is this property that Q of G less or equal to 0. We are really interested in this, and the lemma says that if you are able to find the kernel, then at least it is positive semi-definite. So let us prove it. So let's once again recall the definition. So our Q of X, the sum xi squared minus sum nij xi xj. Here I is less than j. Any order is fine. And xy is the sum xi yi minus the sum, oops, twice, yes, minus sum I is not j, and ij is I yj. Okay, so this is just the definition. And also let us introduce the vectors ei, vector in Z2 cannot be the standard basis vectors, i.e. Eij is delta ij. So here ij are vertices. Okay. Okay. So let us write the value of E, comma, EI, comma, D. So can you tell me what's that? Just E sub I.
Okay, at least it should be
Let's write the formula.
two times di
Yes.
Minus sum by j such that j not equal to I.
Serene, what do you mean J not go to I?
Not equal to I.
Ah, okay.
Uh,
Yes.
ah,
Yes.
but here is some not by pairs but by j's. So n ij
Yes.
dj.
Okay. So this is our formula, and we know that this equals to 0 for any I. Okay. So anyway, so this means that we can somehow express di in terms of dj's, but I claim that now we can show part D. Can we? Actually, maybe I should have written here that D is non-zero. So can we show now part 3?
Yes, we know that the quiver is connected.
Yes.
So each vertex has another vertex which have the same edge, not edge, but
Well, for any
so for each vertex I, there is a j such that nij is not equal to 0.
yes.
It follows from connectedness. So di is not less than nij dj divided by 2.
Right. So now, so we can say that so this means that so di equals to 1/2 sum over j not equal to I, and ij j, and so therefore if di is 0, then for any j such that nij is non-zero, dj is 0. Right, so if we have an arrow connecting two vertices, then vanishing of the coordinate at one vertex implies the vanishing of the coordinates at the other vertex. Now, since U is connected, gi equals 0 for some I implies that dj is just d0 is a vector. Okay, so part 3 is proven. And for parts 1 and 2, we need some computation. Well, it's not that lengthy, but still I would prefer to keep it for the next time. So 1 and 2. Okay, so any questions? So then I stop the screen sharing.